Okay, in this podcast we're going to talk about vapor pressure and phase diagrams. So if you think about leaving a dish of water, let's say, out on your kitchen counter at night, and you get up in the morning and that water's gone, well, the water has turned from liquid to vapor. And obviously it has not reached its boiling point. So there's always some percentage of the molecules, depending on their temperature, that have enough energy that they're able to escape, even though the temperature is not at the normal boiling temperature. And as that temperature goes up, the percentage of the particles that can escape increases. Okay, we call that temperature, or that pressure that's created by the particles leaving the liquid phase and becoming a gas, vapor pressure. So it's the pressure associated with those particles. If you think about that liquid being inside a closed container, let's say like this gas container here, in this case we have liquid ethanol, and some of those particles are going to have enough energy that they're going to escape and go off as a gas. But eventually the system reaches a point where there's what's called dynamic equilibrium, and what that means is the rate at which particles are going from the liquid state to the gaseous state is equal to the rate of the particles that are gaseous condensing and becoming liquid. All right, so the rate of the particles evaporating and those condensing is the same. So the boiling point of a temperature of a liquid is the temperature at which its vapor pressure equals atmospheric pressure. So here we have a graph that shows on the y-axis vapor pressure in torr, which would be the same as millimeters of mercury, and temperature on the x-axis. This is temperatures degrees Celsius. So if I wanted to know what the boiling point of diethyl ether is when it's 400 torr outside, I would just look at the graph and I'd read down. So it would look like it'd be about 18 degrees C. The normal boiling point is when the pressure, the temperature at which the pressure is STP. In this case, 760 torr, or 1 atmosphere. So at standard pressure, the boiling point for diethyl ether is 34.6 degrees C. Just a few terms to know. The word volatile, we talk about a volatile liquid, and what that means is it has high vapor pressure. And if it has high vapor pressure, that means that those particles go from being a liquid to being a gas very easily, which means that there is weak intermolecular forces. As intermolecular forces increases, the vapor pressure decreases because there's fewer particles leaving the liquid becoming a gas. In general, as molar mass increases, the vapor pressure decreases, and that's because, not because the mass is increasing, but as you increase mass, you increase more the number of electrons, and the more electrons you have, as you know, leads to more London dispersion forces. The molecule becomes more polarizable. Now, hydrogen bonding is going to be a greater intermolecular force than London dispersion forces, so it doesn't really matter what the mass is here. If you have hydrogen bonding, you're going to have low vapor pressure and very strong intermolecular forces. And of course, vapor pressure increases with temperature, because as you increase the temperature, you increase the percentage of the molecules that have enough energy to escape. So let's take a look at this chart here. We can estimate the boiling point of diethyl ether under a pressure of 0.8 atmospheres. So if I look at, here I have vapor pressure in torr, so I'd have to first convert the torr. Oops, let me get my pen working there. I'd have to go from 0.8 atmospheres to 1 atmosphere is 760 torr. So I'm going to take the 0.8 times 760. And that's going to be 608 torr, which is going to be right about here. So we want to know what the boiling point is at that pressure. So I just go down from that point, and it looks like it's going to be about 24, 25 degrees C. Okay, so now we're going to take a look at phase diagrams. So these are a little bit more complicated than just the simple heating and cooling curve. What this graph shows you is the relationship between temperature and pressure, and what happens with the phases of matter at different pressures and temperatures. Some people call this a butt diagram for not too subtle a reason. So whenever you see a line here, this is the line between the solid and liquid, and that tells you that on the line the phase change is going on. So this is between solid and liquid, so if I'm going this way, I'm melting. If I'm going this way, I'm freezing. It's helpful to orient yourself first. So the furthest to the left, you're going to be a solid, then a liquid, and then a gas. So what you can see here is that this melting temperature changes with my pressure. So we can talk about the melting point of a substance, but it really is dependent on the pressure. This is the liquid gas equilibrium point, or where the phase change occurs. And you know that's going to change. That temperature is going to change again with pressure. This triple point is where solid, liquid, and gas are all in equilibrium, and there are points under which you cannot have a liquid state, and there you're going to go directly from solid to gas, either through sublimation or deposition going the other way. Few points. So here's the triple point. All three phases are in equilibrium. The critical point is the other point on this graph, and this is where you have liquid and gas coming together and starting to appear pretty much just like each other. You have a liquid that's starting to come apart, or you have a gas that's becoming very dense. There's a nice little video on this playlist that explains the whole phase diagram that you should watch. Okay, so here's again the liquid vapor line. The triple point is where there's equilibrium for all three states. The critical point here, above which the temperature and pressure are, the liquid and vapor are indistinguishable. Okay. So this line told us the boiling point. These lines tell us the melting point. Okay. One of the things that you'll see is for most substances, the phase diagram has basically the same shape, and this line is going to have a positive slope. But what you see with water is that the liquid ice line, liquid solid line, is actually curves the other way. So instead of most lines doing this, the liquid water line does this. And that's because of the really high, the hydrogen bonding, strong intermolecular forces with water. And what it actually suggests is that that as the pressure increases at the temperature below the melting point, the water goes from a solid to a liquid. So you can actually, as you increase the pressure, you go the opposite of what you would expect. You can actually melt a liquid. And on Renee McCormick's NIMSY podcast, she actually shows a little video where you take a piece of solid ice and you put a metal hook in it, and it will actually start to go through the ice. It's that pressure that's causing the temporary liquefaction of the solid. So water shape is unusual. When you think about carbon dioxide, I know we just used it the other day in class when we were looking at the density of the solid and the gas. People tend to think about carbon dioxide not ever being a liquid and always sublimes, but in fact, if you get high enough in pressure, you can have liquid state of carbon dioxide. So a lot of people don't realize this, but every substance you can have solid, liquid, and gas if you have the right conditions of temperature and pressure. So you can look at this example in the book. If we are starting at 0 degrees, which is this line here, and as we move from 1 atm to, as we move from very low in pressure to 1 atm to higher than that, we go from a gas to a solid all the way up through a liquid. Okay. Alright, so we're going to stop there. There are some slides here on solids, and but the words of wisdom from the other AP teachers is these questions have not been asked on the AP exam, so they consider them to be not good use of time to go over them. So you're welcome to read about them in the book, but we're not going to spend time on them. Okay, that's going to do it.